Hi, my name is Kunpeng and I'm from the Hybrid Body Lab at Cornell University. Today, I'm here to present WovenProbe, probing possibilities for weaving fully integrated on-skin systems deployable in the field. I'm also on the job market for a PhD program this year. We conduct a research through design investigation using an extended woven practice for fabricating fully integrated and untethered multi-sensor on-skin systems that are resilient, versatile, and capable of field deployment. While HCI research has developed approaches for the user-friendly fabrication of on-skin interfaces, conducting field studies of these devices in real settings has remained the main challenge. The challenges include the lack of a suitable sturdy substrate that can be worn for extended periods without being bulky, and limitations in integrating an array of miniaturized PCBs, which are critical for sensing and computation effectively as part of the on-skin system. While the common film-based approaches are flexible and stretchable, they often lack the sturdiness and stability to withstand regular wear and tear for longer periods. Garment-based textile fabrication approaches such as weaving, on the other hand, provide a resilient yet slim substrate that can remain unaltered after extended use. Weaving's interlacing structures between two sets of yarns allow organized trace routing for easy integration of distributed PCBs while providing the option for versatile circuit topographies. Merging different woven structures in a single interface offers support to the wires and increased conformity to body landmarks that require flexion. In addition, weaving can bring richness in aesthetic and cultural expression. Our research builds upon related works in three areas. Textile fabrication processes that integrate interactive elements at the surface level, including stitching, embroidery, machine sewing, felting, silk screening, and inkjet printing. While these methods can rapidly augment the textile, they alter the textile only in an extrinsic manner. On the other hand, weaving and knitting afford structural level integration at the yarn level. While knitting is often preferred for stretchable textile worn close to the skin, weaving's fine control of tension and lack of restrictions for materials make it the favored method for structurally integrated smart textiles. The HCI and wearable communities have explored user-friendly film-based fabrication processes to create on-skin interfaces. Interaction modalities include input through capacitive touch, output through thermochromic pigment, haptic feedback, and stiffness change, and sensing through IMUs and string sensing. Current evaluations of on-skin interfaces focus on in-lab bench tests. While in-lab bench tests provide quantitative data of device performance under a controlled setting, they fail to uncover the effect of everyday activities on a device, the social perception towards device usage, the performance of the device when worn on human skin for extended periods, and the effect of body geometries on the device. These factors can only be explored through field deployments. We made the following contributions in the paper. We introduced WovenProbe, a fabrication approach using an extended woven practice for generating a fully integrated on-skin system. We contribute novel weaving techniques underexplored by prior work for a sturdy, versatile, and slim substrate. We conduct a multi-hour continuous wear study of a fully functional on-skin system fabricated with a woven approach to elicit social, technical, and design insights on developing systems for field deployments. And last, the case study of WovenProbe in an index finger and thumb-based IMU tracking system integrated with an NFC coil for wireless charging and data transfer. We adopt a research through design iterative prototyping approach. We will demonstrate the WovenProbe approach through the exemplar of an IMU sensing system that uses 4 IMUs placed on the thumb and index finger to track their motions. The weaving techniques we introduce including lace weaving for conforming to diverse body landmarks, seamless integration of spatially distributed electronic components into thin woven interfaces, and techniques for weaving complex functional elements. Now I'll introduce the 3 aspects in more detail. Firstly, we adopted versatile structural topographies for flexion in the wrist region and around the knuckles. We extend and hand manipulated serpentine Spanish lace technique that exposes regions of negative space and achieves a slim form, which is particularly suited for locations with challenging curvatures or locations that require flexing. Secondly, we developed trace routing for integrating distributed PCBs throughout thin woven structures. The grid-like structure of weaving makes it advantageous for routing groups of wires in a Manhattan routing in both the warp and weft directions, mirroring PCB trace design. Lastly, we explored complex circuit topographies enabled by advanced woven techniques such as double weaving, tapestry, and lace weaving. We developed both a double woven coil with vertical interconnects as well as a slim tapestry coil for RFID charging and data transfer capabilities. Additionally, we used lace weaving to incorporate stretchable serpentine patterns around the knuckles to increase electrical durability. We used a 4-step fabrication process to manufacture our woven on-skin interface. The fabrication process starts with on-body sketching and hand measurements to get a stencil for precise fabrication. The second step is the fabrication of the woven traces. With the stencil created in the previous step, we used a weaving loom to weave extremely thin silk yarns and electrical wires into a slim bandage-like interface. In the third step, we incorporated electronics and applied insulation. The PCB islands were soldered to the exposed end of the integrated woven wires, and we coated a thin layer of silicone as an insulation material to protect the PCBs from water. Finally, the device was adhered onto the skin through a layer of eyelash glue. To evaluate the wearability of an integrated system fabricated with a WovenProbe approach, we conducted a field study where our prototype served as a technology probe. Participants wore the prototype for a multi-hour period, from which we elicited insights on the technical, social, and design aspect of designing on-skin systems. Our WovenProbe hardware system includes 4 IMUs, 2 each on the index finger and thumb, a microprocessor, an energy harvester which is used for power management, an SD card, and a 3.7-volt 40 mAh LiPo battery which powers our prototype. We recruited 7 participants for our field study, which consists of a pre-survey, the wearability study in which participants wore the device for 6 hours, and a post-study semi-structured interview. For the technical assessment of WovenProbe, the MU data for different gestures are demonstrated in this figure. During the field study, the WovenProbe maintained adhesion to the skin over the course of 6 hours for all participants. Slight detachments were noticed towards the fingertips, wrist, and areas adjacent to the electronic components. The device was fully functional over the entire study for all but 2 participants, and no electrical issues were observed. For the social assessment of WovenProbe, participants pointed out how comfortable and desirable they personally felt while wearing the device. Almost all of the participants agreed that they got used to the device after some time, and that it was minimally invasive to their daily activities. In general, participants felt comfortable about the device being seen by other people, and the device easily adapted to the daily routines. For the design assessment of WovenProbe, participants mentioned that the device fitted well to their hands and was low profile and soft. They received positive feedback from all participants for its lightweight, flexibility, and ergonomic form factor, and its ability to easily blend with daily activities. While batteries were used for powering our user study prototypes, they pose certain physical limitations for on-skin interface due to their bulky form factor, finite lifetime, and the need for regular recharge. For our case study, we demonstrate the feasibility of extending our weaving technique to integrate a charging coil to harvest energy and offload data. We take advantage of NFC and offload the battery and data storage to a separate NFC-enabled smartwatch, which serves as an NFC reader. Now, we will discuss the limitations of WovenProbe and future works. Each WovenProbe device was customly fabricated manually for each wearer's hand, which took more than 11 hours from scratch. However, most of the steps can be automated. The use of digital jacquard loom can significantly improve the scalability and speed of the process. Further, by leveraging automated stenciling and pick-and-place operations, components can be efficiently integrated into woven structures. Another aspect is to implement a front-end software design and simulation tool. The confirmability of on-skin interfaces could be improved by using a body scan and computer-aided design tool to model the on-body design of the device, which would then automatically generate a suitable weave pattern and wire size mapping for appropriate body locations. An important move towards a deployable system is making the system waterproof. Well, we have tested the WovenProbe's silicone insulations through a multi-minute underwater test. A more comprehensive study with multiple samples for an extended period of time needs to be performed to confirm the effectiveness of the installation method. We showcase the aesthetic customization opportunities of WovenProbe through two designs: a herringbone twill pattern with its distinctive zigzag pattern, and a Spanish lace design that reveals the skin underneath. By providing a wide range of aesthetic options to fit the wearer's personal preferences, wearers will be able to utilize this intimate on-skin form as a vehicle for personal expression. In conclusion, we introduce our research through design investigations in using an extended woven practice for developing a WovenProbe, a multi-sensor and self-contained on-skin system. By combining complex woven structures and on-skin interface fabrication, we develop fully integrated, versatile, and durable structural and circuitry topographies, which are difficult to achieve using existing film-based fabrication approaches. While we demonstrate our approach in the challenging case of hand tracking systems, we believe it is equally extensible to a wide range of HCI applications that require direct skin contact to access user information. We believe this approach serves as a gateway towards realizing complex and deployable body surface interfaces. Thank you for listening.